Here in chapter 5.3, we will be solving trigonometric equations. Well, what's a trigonometric equation? It's an equation that involves a trigonometric function. To solve trigonometric equations, you will use standard algebraic techniques such as collecting like terms and factoring. Your preliminary goal in solving a trigonometric equation is to isolate the trigonometric function involved in the equation. The process will be similar to isolating your variable in an algebraic equation. So for example, here is a trigonometric equation. 2 sine x minus 1 is equal to 0. The variable that we are trying to solve for, x, is located inside of the trig function sine. Now, there is a related algebraic equation, 2x minus 1 equals 0. Notice that the only difference between these two equations is that the trig equation has a sine x as opposed to just an x. Now, you guys are all comfortable with solving algebraic equations, and here we would begin by adding 1 to both sides of the equation and dividing by 2. The process with our trig equation here is similar, and this actually allows us to isolate our trig function. Well, we add 1 to both sides of the equation, we divide both sides of the equation by 2, and we get sine x is equal to 1 half. Now, we're not quite done. Once we isolate our trig function, we must go to the unit circle to determine the location of the solutions that satisfy the equation. In other words, we need to find the location of the angles that make this statement true. So here is our unit circle. We need to identify the location of all angles that have a sine value of 1 half. Well, sine corresponds to the y-coordinate, so that gives us a spot right here at pi over 6. And we have another solution directly across from pi over 6 at 5 pi over 6. Now, these are not the only solutions to this trigonometric equation. In fact, there are an infinite number of solutions to this equation, because if I were to, say, add 2 pi to pi over 6, I would get another angle that terminates in the exact same spot and would have the exact same sine value. Or I could add 4 pi or 6 pi. Keep adding complete revolutions or subtracting complete revolutions, and that would bring me to other answers as well. The same could be said for the angle 5 pi over 6. Notice if I start with 5 pi over 6 and then add another 2 pi, well, that brings me to another angle that shares the exact same terminal side and the exact same sine value. So there's an infinite number of answers. How do we account for all of these answers? Well, we can say that x is equal to pi over 6. Notice that's our first answer that we got here in the first quadrant, plus n times 2 pi, where n is an integer. Anytime I add on a multiple of 2 pi, that means I'm doing one more complete revolution from pi over 6, or a multiple of a complete revolution to pi over 6, which will bring me to another solution. Or if I pick negative integers, that just means I'm going in the clockwise direction from pi over 6 and doing a complete revolution. So this answer right here accounts for all of the possible solutions that terminate in the same location as pi over 6. Then I must do the same thing with all the solutions that terminate in the same location as 5 pi over 6. To do that, well, we can say x is equal to 5 pi over 6 plus n times 2 pi. Again, any multiple of 2 pi, well, that's going to give me another complete revolution from 5 pi over 6 and bring me back to the same location. So here is what is known as our general solution. This accounts for all of our possible answers to this trigonometric equation. Now, some of you guys might be thinking, well, why didn't we use inverse trig? I agree. If we are here, sine of x is equal to 1 half. If we want to solve for x, we need to undo taking the sine of x, which means we can take the inverse sine of the sine of x. And if I take the inverse sine of the left-hand side of the equation, I can take the inverse sine of the right-hand side of the equation. Inverse operations cancel out. We are left with x is equal to the inverse sine of 1/2. That is the angle that has a sine value of 1/2, which only gives us pi over 6. So inverse trig works, but it doesn't give us the complete picture. Inverse trig will only ever give us out one angle, and there might be multiple solutions. So inverse trig, while it is algebraically correct, does not give us a full set of solutions. So rather than use inverse trig, once we isolate our trig function, we can go straight to our unit circle to find our solutions. Okay, here are some pro tips when you guys are solving trigonometric equations. One, remember that your preliminary goal is to isolate the trig function, all right? Isolate the trig function. Once you isolate the trig function, go to the unit circle. Two, look for opportunities to combine like terms, all right? Think about your regular algebraic expressions. You would combine like terms. Three, look for opportunities to factor. This is a big one, all right? Lots of times you are going to want to factor, and that means factoring out greatest common factors or identify trigonometric equations that are written in the form of quadratics or in the form of other factorable polynomials. One thing to make note of is that whenever you are going to factor something, you must set the equation equal to 0 first. Set equations equal to 0 before factoring. 4, it may be helpful to use fundamental identities, all those identities from section 1 and 2, to help rewrite the equation in terms of a single type of trig function. All right? Writing an equation in terms of one type of trig function can make life easier in some cases. 5, if it is not possible to rewrite an equation in terms of a single trigonometric function, it may be possible to square both sides of the equation to allow the use of Pythagorean identities, which we can then use to generate an equation with one trig function. We'll talk about a specific example where we do this. When you square both sides, you must be sure to check for extraneous solutions, okay? So let's do a few examples here. Solve the following trigonometric equation. Sine of x plus root 2 is equal to negative sine x. Well, recognize that we have a similar algebraic equation. X plus root 2 is equal to negative x. This is similar in that instead of sine x's, I have x's. To solve this algebraic equation, we would begin by combining like terms. We would add x to both sides of the equation, subtract root 2 from both sides of the equation, and divide by 2, leaving us with x is equal to negative root 2 over 2. Our process is similar with our trigonometric equation. We want to combine like terms. Adding sine x to both sides of the equation gives us 2 sine x plus root 2. Subtracting root 2 from both sides of the equation gives us negative 2 sine x is equal to negative root 2. And dividing by 2 gives us sine of x is equal to negative root 2 over 2. Now, again, this is not our final answer. When you are solving an equation, you need to solve for the variable x. But once we isolate the trig function, we can go to our unit circle and identify the location of any solutions, any angles where our sine value is equal to negative root 2 over 2. While sine corresponds to the y-coordinate, angles that have a y-coordinate of negative root 2 over 2 are going to terminate in the location of 5 pi over 4, and also here with 7 pi over 4. So those are the two solutions that are between 0 and 2 pi. However, there are an infinite number of solutions to this equation. There are an infinite number of angles that have negative root 2 over 2 as a sine value. So how do we account for all of those possible angles? Well, we're going to say x is equal to 5 pi over 4. And notice that anytime I tack on a complete revolution, add n times 2 pi, I will come back to another angle that has the exact same sine value. Similarly, we could say x is equal to 7 pi over 4, and anytime I add a multiple of 2 pi, add n2 pi, I am going to come back to another solution. So this is my general solution for our equation. X is equal to 5 pi over 4 plus n2 pi, and x is equal to 7 pi over 4 plus n2 pi.